Quick recap of what we were doing in the last class. We're learning about linear periodically time varying systems, and we'd like to do that in a manner as close as possible to what we are already used to, namely the analysis of a time invariant network. And we took our familiar first order example. Let's say we are interested in trying to solve for the branch currents and branch voltages of a network like this. Oh well, the first thing we do is set up KCL and KVL, and a systematic way of doing this would be to simply write the M&A equations, and if this phasor, current phasor, is denoted by I sub s, then as we saw during the last class, basically we have V1, V2, Is equals 0, 0, and 1, and between 1 and 2 there is going to be G minus G minus G, G, and you will add a plus J 2 pi Fc, and this becomes 0, 1, and this becomes 0, 1, 0, or the other way around, this right. And the phasors, I mean, now you must understand that this 1 here stands for the 1 angle 0 that you are applying here, and straightforward solution of this set of equations gives you the phasors for all the node voltages as well as the branch current. So this is we've seen this already in great detail. Now the question is, what happens when you have a periodically time varying network? So this is G of t, which is doing some periodic variation. Right, and if you look at this, well, one thing we know is that every node voltage and every branch current is now consists of, is of the form sigma some Vk e to the j 2 pi f plus kfs times t, all right. And if we kind of assume that, well, for sufficiently large k, perhaps this Vk becomes so small that you can neglect it, and therefore you denote this branch voltage, right? You express this as the phasor corresponding to that branch voltage is something like this, where you start off with V0, V minus 1, V plus 1, blah blah blah, V minus k, capital K, right, and V plus capital K, and this is basically a column vector, and since writing the stuff here seems awkward and much easier to write the stuff this way, it's minus Vk blah blah blah, V0, sorry, not minus Vk, this is V minus k, blah blah blah, V minus 1, V0, V1, this is capital K all the way up to V capital K, and this transpose. And this underscore is just there to kind of remind ourselves that this is a vector. And likewise, every current will now be characterized by these every branch current, which in the time invariant case was only characterized by one complex number, is now characterized by 2k plus 1 complex numbers, right? And there's no point in complaining about it and saying, you know, I mean, this seems terribly complicated, but that's what life is, right? I mean, the network is varying with time, and it seems reasonable that you know, if you have something which is varying with time, to capture its behavior, you need, within quotes, you need to work a lot harder, right? So fortunately for us, KCL and KVL must be satisfied not merely at a frequency f, it must be satisfied at every frequency of the form f plus k times fs, right? And that therefore means that, you know, while early in the linear time invariant case you had 3 equations in 3 unknowns, now, so I'm going to write this down here. So 3 equations in 3 unknowns, and all of a sudden now what comment can we make? So how many equations do we have? And we need, so if KCL KVL had to be satisfied at one frequency, we needed 3 equations, and you know, we had 3 unknowns per frequency evidently, right? So now you have 2k plus 1 frequencies, so you basically have 2k plus 1 equations in 2k plus 1 unknowns, correct? So already, as you can see, even a simple first order RC circuit, as soon as you make the resistor time varying, the complexity of the calculation becomes kind of insane, right? But fortunately, I mean, once you understand the principles, you go to a computer and then invert these matrices, right? Okay. So now, how do you write KCL and KVL? We can write this in the same, it turns out, as we will see going forward today, that we can use the same formulation that the MNA formulation that we used for the time invariant case. If you know to do that, then this just becomes very straightforward to write the set of equations. The solution, of course, you know, you punch it into MATLAB or your favorite tool and then get the answers, right? And just like you know, well, you see a complicated network, and yeah, you know that if it's a linear network, I can actually do the math and get the answer. But you go to a computer anyway for, you know, if the order is say 2 or 3 or 4 or something, you know, you don't basically start doing stuff with pen and paper. You go to a computer. It just so turns out that when you have a time varying network, even for a first order system, right, you need to go to a computer, right? That's how life is. So as far as we are concerned, we are more interested in figuring out how to write the equations in a systematic way, and we will be very happy if we are able to link it to what we did with the time invariant case, correct? So you don't want to learn a new set of rules now. Okay. Great. So let's go element by element. I mean, so therefore, remember in the time invariant case, we wrote the MNA stamps for each element and built up that G matrix by adding the corresponding MNA stamps, correct? So we have to do the same thing here too, except now that we have to deal with the fact that, if you have an element, say for example, this is G of t, which is varying periodically with at some rate G of t plus Ts, then you basically need to be able to relate the voltage phasor with you need to relate the current phasor with the voltage phasor, correct? So the branch voltage will be of some form like this, correct? So let's call this node A and this is node B, and the branch voltage, so that's V AB, right, or VAB of t will be of the form some VAB k sum over k e to the j 2 pi f plus k times fs times t. Likewise, the current IAB of t will be some IAB k e to the j 2 pi f plus kfs times. So, the VAB phasor is simply nothing but we, as usual, we will truncate this beyond a certain large number k, which can be made arbitrarily large. So, you have VAB of minus k blah blah blah, VAB 0 blah blah blah, VAB of plus k whole transpose, right. This is a column vector, and likewise IAB, the phasor vector that we are now interested in, is simply IAB minus k blah blah blah, IAB 0 IAB 0 blah blah blah, IAB plus k. All right. Now, the question is, how is VAB, how is IAB, how is the vector IAB related to the vector VAB, right? How is, in other words, how is IAB of t related to VAB of t? IAB of t is simply nothing but G of t times VAB of t, correct, and G of t is nothing but, you know, it's periodic, and therefore, well, can be expressed by its Fourier series, which is G sub k, or let me use another subscript, G sub L e to the j 2 pi L times Fs times t. This is simply the Fourier expansion. Correct? And again, we can truncate this expansion for, you know, beyond a certain large number, right? That we can set later, right? At this point, we know that, I mean, all that we need to understand is, well, you know, as far as engineering practice is concerned, presumably all the infinite coefficients are not important. We probably, you know, stop somewhere. So, therefore, I of t therefore must be, well, GL e to the j 2 pi L Fs times t times VAB k, this is sum over L, this is sum over k, e to the j 2 pi f plus kfs times. Correct? Does it make sense, people? This is nothing but g of t, and this is nothing but VAB of t, and all that this is saying is that current is G of t times the voltage. Now, the question is, what is the so we are trying to relate the current phasor, which is basically IAB of the minus capital K, right, all the way. Let us say we try to find the strength of the minus kth, capital Kth harmonic in the current phasor I. Clearly, it must be related to the strengths of the voltage phasors. So, VAB minus K blah blah blah, V0, this is IAB 0, IAB plus K, this is VAB plus K. So, what comment can you make about IAB of minus K? That is, anyway, please remind me what this actually signifies. What does that number indicate? It represents the strength, the complex amplitude of the current at a frequency F minus capital K times uppercase K times Fs, right, and likewise for every one of those terms, and in specifically IAB 0 quantifies the complex amplitude of the current at F, all right. Okay. So, what comment can you make about IAB of minus K in terms of VAB of minus K? Well, what does VAB of minus K signify? Well, it signifies the complex amplitude of the voltage at frequency F minus KFS, right? With what, how will that reflect as the current at the same frequency? This is at a frequency F minus KFS, correct? This is also at a frequency F minus KFS. So, what should be this entry here? I mean, which two terms? I mean, this term is VAB of plus K e to the minus K e to the j F minus KFS. If this has to be the same frequency, the only term that has, I mean, so this frequency, the G term, that, remember that when you multiply two of these terms, what you get on the left hand side is simply the sum of those frequencies, right. So, if the right hand side, if I or V has got a frequency of F plus KFS and the left hand side has the same frequency, the only term that can cause it is the G0 term. Is that clear? Yes, no? Yes. Okay. So, this is G0, very good. What comment can you make about the second column in the first row of this matrix? What is the second term here? Will have a frequency of, sorry, this is not, this is capital K, yeah. So, this will be F minus K minus 1 times Fs. So, that will have, if that has to result in a tone at F minus KFS, correct, what is, what should you multiply it by? G. The input tone is F minus K minus 1 times Fs, yeah. So, basically the frequency is jumping by plus 1 Fs. So, that the only way that can happen is if you multiply it by G1, G minus 1. Yeah, sorry, G minus 1. Correct? And so on and so on and so on. Finally, the last term will be G minus 2k. All right. Okay, let's go to the second row. What comment can you make? So this would be the second entry there would have a frequency of f minus k minus 1 times fs, and this is f minus kfs. So this has to go, is the output frequency greater than the input frequency or the greater? So what should we have? G plus 1, right? And then this would be the diagonal, the second row, second column will be G0, very good, blah 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 blah. And what is the last? So I guess you see the pattern now. G minus 2k plus 1. Correct? All right. So now it doesn't take a genius to fill out all those other entries. So what will be the last entry here? G 2k, very good. Blah 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 blah. This will be G. Okay. And by the way, g of t is a real function. So g of L must be equal to g of t is a real function, correct? So the Fourier coefficients must satisfy conjugate symmetry. So basically g of g minus L star. Okay. Does it make sense? Okay. So now I am going to call, see what happens. The I phasor therefore is, in the time invariant case, the current phasor was simply G times the V phasor. Now the I phasor is now a vector, and that is a G matrix multiplied by VAB. Correct? Does it make sense, guys? Okay. So apart from those underscores below each one of those terms, the equation looks pretty much the same as it did for the time invariant case. Does that make sense? All right. Now, out of the question I am going to ask you is, well, this G of t had this conductance matrix G. Now, if I transpose G, remember this, what kind of matrix is this? G matrix, this small g conductance matrix for this conductance. What kind of matrix is it? It is square with size 2k plus 1 cross 2k plus 1. Now the question I'm going to ask you is, if I transpose this matrix, evidently that corresponds to some other conductance, right? The question is, what does that correspond to? G of minus t. Right, just something to keep in mind, right? We'll use this later, okay? But it's a simple observation that, all right, excellent.